Robots need sensors to sense the environment. You can imagine that there are a lot of sensors around. Sensors measuring magnetic fields, light, sound, etc. In this video, I will show some sensors that are commonly used in robotics. It really depends on your application to decide which sensors are useful for your robot. A sensor measures a physical phenomena from the environment and produces an output signal. This cannot be done continuously, so the sensor will have a certain sampling frequency or resolution in time. Sensors might also have a resolution in space, for example the number of pixels in a camera, or the smallest distance difference in a distance sensor. Other specifications of sensors include accuracy, precision, repeatability, and latency. When working with sensors in the real world, you will encounter that the signal produced by the sensor will be noisy, but you might also encounter aliasing errors. In robotics, sensors can be used in three ways. When measuring properties of the environment, we talk about exteroception, for example a camera. But a robot might also need to know some properties about its internal state, for example the state of the battery. This is called interoception. And lastly we have proprioception. This is the measuring of self-movement and location. Wheel encoders, or IMUs, are examples of this. Apart from what to measure, sensors also differ in their way of how they measure. Passive sensors just measure a property of the environment. Apart from this, robots can also use an active sensor. Active sensors send out a signal to the environment and measure its return signal. By measuring the distance in time or strength of the signal, the sensor can deduct useful information. Humans only have passive sensors, but bats are known for their echolocation, which is a way of active sensing. Active sensing can give you a lot more information, but has the downside that it costs more energy and that the multiple sensors might interfere. Let's have a look at some commonly used sensors in robotics. One of the mostly used sensors is the camera. They are cheap and a lot of research has been done on processing images. And we're not limited to the visible light frequencies, but we can have multispectral cameras looking into infrared frequencies as well. The downside of a single camera is that it's really hard to deduct depth information from it. This is why in passive camera technology we also have stereo cameras, which use triangulation to get depth information. This can of course also be done with one camera, but uses multiple images over time to deduct this information. This is exactly what doves do. They constantly move their head back and forth, basically creating two images from different perspectives and getting depth information from it. Another commonly used passive sensor in robotics is the IMU, or Inertia Measurement Unit. This device often consists of accelerometers, gyroscopes, and magnetometers to deduct its orientation and acceleration. In robotics, this is mostly used for proprioception. Of course, there are more passive sensors which can be mapped to human senses. The use of microphones really depends on the application. A lot of robots do not need to interact using speech, so the use of microphones is not needed. Bumpers are also used, but mostly as a last resort to not bump into things. Of course, there are also technologies for smell and taste, but they are notoriously hard to engineer. Most of the time, not too useful for robotics. Humans mostly use smell and taste to identify hazardous food or surroundings with limited oxygen in order to survive. Both are not an issue for robots. Robots can also use passive sensors to measure properties in the environment. Let's have a look at some. One of the most well-known active sensors in robotics is the LiDAR, or Light Detection and Ranging Sensor. This sensor sends out a laser pulse and waits for this pulse to get back. Based on its return time, also called time of flight, the sensor knows the distance to an object reflecting this signal. The easiest way is a single static point. More commonly used are LiDARs scanning a plane in 360 degrees by rotating the LiDAR beam. This can generate a map of the environment. An even more complex LiDAR might also tilt the beam, creating a 3D image of the surrounding. A LiDAR works great on any material reflecting light. Black surfaces, mirrors and glass can produce errors. Modern LiDARs use solid-state technologies, not using rotating parts anymore. Instead of sending out a light beam, the ultrasonic distance sensor sends out an ultrasonic sound and waits for the return pulse. Also with the goal to detect the distance of objects. Other than the LiDAR, this sound produces a wave and therefore will detect any object within this beam called field of view. It will therefore not know the direction of the object. Since this is limited to the speed of sound, the frequency of this sensor is not too good. Another downside of using sound is that not all materials reflected in the same way. Objects that damp sounds, like curtains, but also some clothing, might not return any signal. Yet another way of getting distance information of objects is radar, or radio detection and ranging. Like the ultrasound sensor, it sends out waves only this time in radio frequencies, using an antenna. In a static basic version, it is not able to detect where in the field of view the object is. Like the light in a LiDAR, the radio waves travel with the speed of light. The advantage of radar is that it is also possible to detect the Doppler shift. With that, it can measure the speed of the object in the direction of the wave. This is of course also used in speed cameras. The reflection of radio waves depends a lot on the frequency used, but usually water and metal are heavily reflected. More complex radars might use frequency modulation in order to detect range and Doppler continuously, so without sending a pulse. They might also use phased arrays, multiple radars with a phase shifter to steer the radar beam without the need to physically turn around. With this, we discussed 3 different sensors, all actively measuring distances to an object. It really depends on the environment which one is better suited for the robot. We also discussed you can measure distances with stereo vision, but there's also an active way to get distances in camera images. An active depth camera is a camera with the ability to measure the depth to objects in the camera image. It does this by sending out an invisible infrared dotted pattern called structured light. This pattern can be seen by the camera and will be deformed depending on the distance to the reflecting object. Knowing the pattern of the original infrared dotted pattern, the camera can calculate the distance based on the deformation seen in the image. Depending on the frequency used, this sensor might only work inside, since the infrared light of the sun might interfere. Detecting depth to objects is really important for robots to know where they are. There are 2 other sensors that can also be used to know the location of the robot. The most well-known sensor to get the location of a robot is GPS, or Global Positioning System. By using triangulation on radio signals coming from satellites, it can measure its location on Earth with an accuracy of about 10 meters. This can be upgraded to around 2 meters when using differential GPS, or DGPS, which uses ground stations to account for the imperfections in the signal. Although GPS is free, you would need a subscription for DGPS. Since GPS always needs at least 3 satellites in line of sight, it will not work indoor. Indoor navigation is therefore still a hard problem. In order to being able to know where the robot is without GPS or depth sensors, robots use wheel encoders. Wheel encoders measure the rotation of the motors. This can be done by measuring slots in a disc using light, but it can also be done by measuring whether magnets on a disc are seen. The robot can use these wheel encoders as proprioception in order to know where the robot is. This is called odometry. You can imagine that the odometry is far from perfect, and errors will accumulate over time. With this presentation, I hope you got a bit of an overview of the types of sensors that are commonly used in robotics and what their advantages and disadvantages are.